Okay, thank you, Dani, and thank you for being here. As you see, it's a joint work with colleagues from Potchefstroom, who work very much in operational risk. So I'm on the fringes of operational risk, and my focus is more on the extreme value application, or the use of extreme values in that. But I will say a little bit about operational risk. So just an overview with 8 points. I'll start off by giving a background on operations research, operational risk as motivation for the research. Okay, and say a bit about that. One of the things used in operational risk are certain approximations. So I'll say something about that. And then get to EVT. And essentially what we do is to use these approximations and base them in using extreme value theory to estimate quantiles. But I'll explain that in more detail. And then, of course, you have to get to the actual estimates. I'll explain that. I'll give a quick application, mention some conclusions, few points for further research, and then references. Okay, a few points on operational risk. This has to do with unexpected losses, all kinds of losses due to people, due to systems, due to fraud, internal and external. So it comes in many different forms. And in the same way as market and credit risk, you have to budget for that happening. And there's a particular approach, the loss distribution approach, that I'll say more about that. But for that's required a 99.9% quantile, which is then a particular value at risk. So that's very, very far in the tail. And especially in operational risk, where the data is not overly available. So one has to be careful in how you estimate that. Now, what's worked with is the so-called aggregate loss distribution. And it's essentially the same as being used in insurance, short-term insurance. You have a number of claims, stochastic number of claims, and you want to look at the total claim size. Here you have a number of losses, stochastic number of losses, and you want to look at the total loss per year, working on an annual basis. Now, the two distributions you work with, the one is the size of the losses, which is called the severity distribution. And the second one is then the number of claims, which is the frequency distribution. And so you have a random sum of all the losses, but a random number. Okay. And of this aggregate loss distribution, you want to have this very extreme quantile, 99.9. So that's the issue here. What's been done up to now is essentially to fit distributions for the severity distribution and the frequency distribution. And then you have a sum, a random sum with known distributions, if you fitted these. And then you use simulation to estimate the quantiles. So you just simulate, but it's very time consuming and computer intensive. So several approximations were suggested, and two of these are particularly interesting and particularly powerful. The one is called a single loss approximation that I'll say more about, and the other one, the perturbative approximation. Single loss in the sense that instead of having these a random number of losses, in other words, a distribution of a random number of losses, you have a single loss for which you find the quantile. And essentially the same for the perturbative method. But what they do is they move from the aggregate loss distribution of the random sum, to the severity distribution. So instead of getting the quantile of the aggregate loss, you get the quantile of the severity distribution. The problem is you move from a very high quantile to a very, very high quantile. So whereas you need it at 99.9, you now go much further in the tail than that. So it's taking you far away from where you have a lot of data. And the work being done depends on many factors, or the accuracy of the estimates, but the most influence is by the severity distribution. And so the severity distribution and the severity distribution that you use, if you fitted it, that has the most influence on the accuracy of your quantiles. And many found that several distributions give a similar goodness of fit. So and we'll see that later. If you have your goodness of fit measure, they're all more or less the same, which says, well, if I base it on goodness of fit, I can more or less use any of them. But if you calculate the value at risk estimate, then they keep different paths. Okay, so that doesn't always work so well. So what do we do? Well, essentially we say, try and non-parametric approach based on extreme value theory. Because extreme value theory gives you a nice basis on which to base this. And what we do is to use those approximations that I've mentioned, for which you need this severity distributions quantile, to estimate that quantile in a particular way. And that's all non-parametric. So we don't have to go to a particular severity distribution. And it's a fairly simple idea. You want to estimate something very far in the tail. So you go deeper into the data, you estimate it there. We usually can estimate it fairly accurately. And then you multiply that estimate with a so-called multiplier to get to this. Now, of course, the multiplier is in the critical thing. And that's where extreme value theory leads us. So it's theoretically based on extreme value theory. Now, both these methods, single loss approximation and the perturbative method, they have a first order and a second order. And extreme value theory, you'll see we have first order and second order and higher orders, but I'll stick to first and second. So we have the combinations of the approximations, first and second order, extreme value, first and second order. So you have all these combinations that you can try out. And the methods that we propose work very well compared to the standard measure. The main advantages are that it's non-parametric, and of course that its computing time is much, much lower. It's essentially a plug-in estimate. Because for the other methods, you need these Monte Carlo simulations, and that's quite time-consuming. Okay. So that's just an introduction. So our issue is operational risk that needs this very high quantile. The current methods try and fit the severity distribution and the frequency distribution, but the big issue is the severity distribution. So we try and get away from that. But if you look at the problem, we have a sample from some distribution F, and we'll assume it's IID, and that's called the severity distribution. Then we have a number of losses, and we'll assume it's Poisson distributed. There are good reasons for using Poisson, but there are alternatives. And then we're interested in that random sum. In other words, the total loss of those n losses. And this is over an annual basis. And that's, as you know, a compound Poisson distribution. So if we call that S and its distribution G, then G is compound Poisson with the two parameters F and lambda. And what we're interested in is this high quantile of G. In other words, G inverse at 1 minus P for P small. In particular, talk about 0.999 for 1 minus P or P 0.001. That's a very high quantile. So that's the formulation. Now, if we just say something about the approximations that I've mentioned before, I'm not going to go into any detail. The first one is the single loss approach, originally proposed by Booker and Klippelberg, which said I can approximate G inverse 1 minus P, what I require, by F. And remember, F is a severity distribution at the 0.1 minus P divided by lambda. And lambda is mostly an integer, and it could be a large integer, 20, 50, 100, which means that I divide that P by a fairly large number. So I make it much smaller, which means I go even further in the tail than I need it over there. Okay, so it really takes you far into the tail. Then this was extended to a second order by Deegan. And depending on whether the mean of the underlying distribution is finite or not, you just add a lambda times mu, or you add a more complicated constant. But the main point is still getting that quantile. The others are just terms that you can estimate from the data. The second one is the perturbative approach from Hernandez and his co-workers. And you can go up to any order. We're not going to go too high, but essentially your first order is just your zeroth term of the perturbative. Now, if you look at that, Q naught, it's again F inverse at 1 minus log 1 minus P over lambda. Now, again, that takes you further than P. Okay, it again takes you just like the P over lambda. It takes you to a much smaller point, so you go much further into the tail. We can adjust for second order using Q1 and Q2. So your second order approximation will be Q naught plus Q1 plus Q2. And Q1 and Q2 are dependent on a number of things, amongst others, and I'll say more about that a bit later, on the density corresponding to F, severity distribution, and the density's derivative. So it's quite a bit of work. But if you look at this, it says we're working with truncated moments. Both the first moment and the second moment are truncated at Q naught. So then the question is of an X with an infinite mean or infinite second moment does not come into play. We always truncate, so it's fine. Okay, so we want to use EVT to estimate those two quantiles that are needed in these approximations. Okay, this one from the single loss and this one from the perturbative. So the idea is, as a basis for what we aim to estimate, this one or that one, we want to use extreme values. What they do in this case, as in other cases, they have this quantile they have to estimate. They fit an F, in other words, a goodness of fit find an F and a lambda from some distribution on the number frequency distribution, and then they simulate to estimate that. And that's quite computer intensive to obtain that. Okay, so now we get to the EBT, which is really what's exciting for those that like EBT. But for that, we need some notation, right? And unfortunately, one has to keep the notation to a certain level, otherwise, you don't follow really. First of all, we all know the quantile function as the inverse of the distribution function. There's something called a tail quantile function, which is a transformation of the quantile function in this way. You can also think of it as a reciprocal of the inverse of the survival function. Okay, but it's this. So we shift the argument from 0 to 1 to this, which gives us from 1 to infinity, which means we work also at infinity. And there are some mathematical reasons why it's useful to have infinity included and not work on a bounded interval. So that's a tail quantile function, and it plays an essential role in EBT and certainly in this work also. What we must always keep in mind is we're interested in Q1 minus P, the quantile at this level P, but that's equal, if you look at that, to U1 over P. So for small p means 1 over P is large. So whereas you have a small p, in other words, Q close to 1 on the upper bound, here you move to up to infinity for 1 over P. So the smaller p, the higher you go up. Okay. And then based on that tail quantile function, there's a very basic condition. It's called a domain of attraction condition. And it's in terms of the tail quantile function. And it says that there exists a positive function A such that this quantity, in other words, the tail quantile function at the point xt minus tail quantile at the point x divided by this function A at x, that converges. The condition really says this quantity converges. What is then shown, if it converges, it must converge to this. That's the only limit that it can converge to. But the assumption really says there exists a function A such that you have convergence of this. And then the limit must be that. This gamma plays a very critical role in extreme value theory. It's called the extreme value index, and it's a real constant. So it can be positive, it can be 0, it can be negative. And what we're going to do is to say, well, if you remember that U1 over P is Q1 minus P. So if we think of XT as 1 over P, okay, then we essentially have Q1 minus 1 over XT there. So that's very far in the tail. If we think of X as 1 over some other P deeper into the data, then we can write this for large X as UXT approximately UX plus AX times the right-hand side. Okay. And on the left-hand side, you have what you're aiming for. On the right-hand side, you have your UX, which you get from deeper into the data, another quantile, and the others are just parameters. But I'll explain that. But that's the basic idea. Now we're going to focus on gamma positive And then all kinds of nice things happen here. In particular, the function A then has a specific form, and the whole thing becomes much simplified. Okay. Just note that for gamma 0, we take the right-hand side as log U. And this condition holds for most distributions that are useful in applications. So it's a very, very widely applicable assumption. And also, it's the basis for two major theorems of extreme value theory. The first one is Fisher-Tippett, which gives you the limit, essentially, of the maximum of a sample. And it says that the limit can only be a particular distribution with generalized extreme value distribution. So it's a nice, clean theorem, which is almost like the central limit theorem that says if I have an average, then the only limit can be, in the certain conditions, can be the normal. Okay, here we have the analog of that. The only limit of a maximum under certain conditions can be the G, generalized extreme value. Because Baltimore de Haan looks at a threshold and then the exceedances of a threshold, conditional exceedances. Given that you've exceeded, what's the distribution of that exceedance? And that, again, leads to a particular distribution, which is called a generalized Pareto distribution. So the basic condition really leads to very basic theorems in extreme value theory. And we'll briefly come back to the Pickens-Baltimore de Haan at a later point. Okay, for gamma positive, as I said, things become much nicer. And keep in mind that positive gamma means heavy tail distributions. And often we're interested in financial applications in heavy tail distributions, in which case AX has a nice form. We can choose AX as gamma times UX, gamma times the tail quantile function. And that means that if we take UTX over UX, remember in our basic condition, the limit of that is T to the gamma. Now, functions of this form can be written in this form. If a function is of this form, we can always write it as a power function, x to the gamma, times the so-called slowly varying function. That's well known from the mathematics of this type of function. Now we have this, so we can write our function, our quantile function in this form. And this L is slowly varying, which says if I take that function at those 2 points and x goes to infinity, it goes to 1. For all t positive. Now, a function u of that form is regularly varying. And the class of regularly varying functions is very powerful. There are all kinds of very powerful results for that. So we can now say under this condition, we're in the class of regularly varying functions. Okay, so we can use all the theory and results from regularly varying functions. Now, all of this says if I take UTX over UX and I use this fact over there, then it simply says it's equal to T to the gamma, because the x's cancel, times the ratio of those slowly varying functions. And what we're going to do in our applications will be to do one of two things. First of all, for a first order, because this ratio goes to 1, one can approximate it by 1 and say this is approximately T to the gamma. Or you can go further and say, can I place some form on this ratio? Okay, is there a natural assumption to make about that? And we'll see that's true as a second order condition. And in that way, we'll get first and second order conditions. Because if we look at this, UTX is approximately then UX times T to the gamma times this ratio. Okay, so the second order condition. And if we look at this first order condition, it said if we look at UTX minus UX over AX, then we assume it converges, and if it converges to that function. Now we say, what's the rate of convergence? In other words, if we subtract the limit, can we take that quantity, which we now know goes to 0, multiply it by another function that goes to infinity, so that this goes to a new function. Okay, that's not 0 or infinity. And that's the second order assumption that says there exists a function d, with d going to 0, such that, and the function k, such that the limit of 1 over d, now 1 over d, and then of course goes to infinity, times the square bracket, which is just the difference between the first order condition minus its limit. The square bracket goes to 0, so that this limit is again a new function. So it's not 0 or infinity, it's a new function. Okay, and it can be shown that this function d, if it exists, it's necessarily regularly varying. Okay, so regular variation of order rho, and this rho is negative. Whereas previously we saw that u, in the case gamma positive, is regularly varying of order gamma, for that gamma positive. K can be expressed in terms of H gamma and H gamma plus rho, but we don't need it, so I'll just leave it there. Okay, so this is our second order assumption. If we again make the assumption that gamma is positive, a special case of interest, then under the second order condition, it follows that log of that slowly varying function on u satisfies this basic condition that we started off with. Okay. The basic condition was C gamma A, with A the auxiliary function and gamma the parameter. Here it's C rho D, with D that multiplier in front of the square bracket, and rho then the order of the regular variation of D. Okay. Now that log LU satisfies that, simply says I can take log LUXT minus log LUX divided by this auxiliary function, and I'll end up again with this kind of thing. Now, what does that help us? Remember we had previously, we said that we could take UTX over UX as T to the gamma times LUX over LTX divided by LX. Now we say, if we take that ratio of the slowly varying functions, then we can write it as E times the log. And the log of the ratio, of course, is log of the differences. And now we apply that. Okay? Because this says log of this minus log of that is approximately dx times h rho. So we write it as exp log difference, and then approximate that log difference with dx times h rho. So now we have an approximation for the ratio of those two slowly varying functions, and that will lead us to a second order. This thing is small, I can take it out. We will use that in the second order multiplier when we get to the multiplier. I have to watch the time also. Okay, now to get to the multiplier method, as I've said before, the idea is if we want to estimate a very large quantile, we try and go back to a quantile deeper into the data where we have enough data to estimate that quantile, and then we need a multiplier to get us from here to here. But we don't want to take any multiplier, we want to have that multiplier based on solid theory. And that's what extreme value theory gives us. Okay, so we go back to the basic condition, and we're interested in that. Just to repeat that. And then we go, and I'll focus on the gamma positive case. We saw that UTX over UX is of this form. Okay, and UTX can then be written as just UX times that. Okay. And since that goes to 1, to first order, we can write UTX as that quantity, and then we leave out this, which goes to 1. Okay, so our approximation for UTX is UX times T to the gamma. And now we want to bring that into the estimation of the quantiles. So we take X large. Remember, this is as X goes to infinity. So we take X large, and then T is also potentially large. So TX is larger than X. So we take TX as 1 over P. And we take X itself as 1 over P star, with P star larger than P. Okay, so if we take those two together, T is P star over P. And that says we can approximate, if we go to this, we need U 1 over P. Okay, that's what we need to estimate. We can approximate that by P star over P, that's T to the gamma, times U 1 over P star, okay, which is X. So this P is very small. Okay, so we sit very high up. P star is larger, so 1 minus P star is deeper into the data. This we can then estimate, and this is just constants with the parameter gamma. Okay, so that's essentially what we do to first order. For second order, we just use what we've seen, where we get this added to T to the gamma. Okay, so LUTX over LUX can be approximated by that, and then UTX is approximately this. And again, if we make those choices, TX 1 over P and X 1 over P star, then what we need to estimate, U 1 over P, is the same as what we had before, P star over P to the gamma, but added this term. Okay, and then again, something we can estimate. Okay, so if you leave out this exponential term, you're back to your first order. Now, what we need to apply this is estimates for all the parameters involved. Now, there are the two clear parameters, gamma and rho. Gamma from that first basic condition, rho from the second order condition. D is a function, auxiliary function from the second order, but we need it only at a single point. So we don't have to estimate the whole parameter, the whole function. We can just consider this as a parameter. Okay, and then the one thing we need is this. That's now our quantile that we want to estimate, but more into the data. Okay, so this is what the main estimate then is. Now, I'm not going to dwell too much on this, but you might remember if we have data and we have the order statistics, we have a quantile function, then we can always estimate the quantile function by the empirical quantile function, the same way that you estimate your distribution by your empirical distribution function. And what that says is I can estimate my quantile function by my empirical quantile function, which is essentially the order statistics. Okay. So if I want to estimate this U at that point, which is Q at a different point, then I'll write 1 over P star. I choose P star as K plus 1 over N plus 1. Okay, so we have N large, we have K less than N, so P star is K plus 1 over N plus 1. And we can estimate U hat 1 over P star by that particular order statistic. Okay, so that immediately gives us an order statistic. Of course, we have to choose K. Okay. But if we have a K, then we have an estimator that we can use in our multiplier. Okay, so to first order, we estimate U1 over P, which is what we need, by K plus 1 over P n plus 1 to the power gamma, which we estimate by gamma hat. And that we also estimate by an order statistic. Okay. Now, if we choose a particular estimator for gamma, and there are many of them, as a so-called yield estimator, then this is a well-known estimator, the Weissman estimator. And you see what we do, essentially we estimate the pth quantile, or 1 minus pth quantile, and to estimate that, we go deeper into the data with this as an estimate of a quantile times essentially then a multiplier. Okay, so this is just what happens. Okay. For the second order, we just take what we had before. We have the same k plus 1 over pn plus 1, the term over there. And then we have this extra exponential term. Okay. But now we have more parameters. We have the d function at 1 over p star with p star k plus 1 over n plus 1. We call that d and k. And we have rho, which we have to estimate as a second order parameter, times then that. Okay, so this is then the second order multiplier that we have. Okay, now once we have the multipliers sorted out, we have to get to the estimates, and I'll just briefly explain that. Remember that we had the two approximations, and I'll just look at the first order. I'll say something later about the second order. For first order, the single loss approximation, we need to estimate F inverse 1 minus P over lambda. Okay. With P a given value, say 0.001, as in operational risk, and lambda some integer value that might be fairly large, up to 100 or more, depending on the number of losses you're working with. So that becomes quite a small number. In the same way, for the perturbative approximation, we work with this. Again, a very high quantile. Okay, and then I just write down to second order, we have this, where we just add that if mu is finite. If it's infinite, then it becomes more complicated. For this, we have this one, and this one of the problems I had with the PowerPoint. It cut off, but there's another term, f at little f at q naught times q naught squared, but it cut it off there. I'll correct that. Okay, but this is what we need for the perturbative. And we need, in those cases, we need this and we need this. Okay, so those are the two quantiles that we really need to estimate with our multiplier. And in this sits various parameters that I'm not going to go into the estimation. They're the extreme value theory parameters that follows from the extreme value theory application. And those are fairly standard, not particularly easy, but standard in terms of that there are well-known ways of estimating them, especially with bias reducing estimators because of the bias that creeps in extreme value theory. So they are well established. On the other hand, in the perturbative method, you might have remembered, and I'll just go back. You see there sits an F there, and there sits an F prime there over F. So in the perturbative second order, we need also F little f and f prime. Now we need that at the point q naught. And q naught is quite a high quantile. So we need the estimate of the density and its derivative at a fairly high point. Now, we have no data or little data at that point. So to estimate it there is not easy. What we did was, and now I have to go back to the Pickens-Walkeman-de Haan theorem. which gives us the limit of the conditional exceedances. But from that, you can derive an approximation for the distribution, the underlying distribution far in the tail. Okay? You can take it into the tail. And what we did was to take that estimate, in other words, the generalized Pareto distribution, take its derivative and take the derivative, second derivative of F, and use that. And it worked quite well. Now, it's quite unexpected, because you can think you're going down, down, down in this far tail. But of course, the GPD, generalized Pareto, goes far in the tail. But to think that you would have a good approximation for the density of F and its derivative was a bit unexpected, but it worked well. It very well gave good results. Okay. And then we also needed those truncated moments, but estimating truncated moments is not difficult. You just take the average of all those truncated points. So it's either the first truncated moment or the second truncated moment. So that's quite easy. Okay, so that's a theory. In the application, and this is very much my colleagues in Potchefstroom that did that, but I'll talk on behalf of them. They use data from the SAS database. SAS has a database of operational risk that they gather from all over the world, and it's available. So we use data from that, and in these operational risk, you have different lines, business lines, and within a business line, you have event types, and so on. And there are more or less 8 business lines. One of them is retail banking. And then within that retail banking, we have all kinds of event types. So this is for the retail banking line. And the event type is execution, delivery, and process management. So it's a particular type within that business line. There were 23 observations over 61 years. Since we're working with an annual rate, it gives us 5.3 per annum. So if you think of the P that we're interested in, was 0.001, we now have to take 0.001 divided by 5. Okay, so that's a factor of 5 smaller, which is then very small. Now, I mentioned before that the traditional methods, they fit a severity distribution and also a frequency distribution. Once you have that, you can simulate the quantile that you need. Very computing intensive, but the problem is that you often have the same goodness of fit measures over different distributions, but they lead to different operational risk estimates. So, for instance, in this application, there were 3 possibilities. There's a Burr distribution, which is popular in extreme value theory. There's a log normal distribution, which is quite popular in operational risk. And then there's a splice distribution, which is take the log normal in the center of the distribution, and you splice it at a particular point, and you use the GPD, generalized Pareto distribution, for the tails. Okay, so you fit them together nicely, smoothly. And for the tails, you know what's happening there. It's a GPD. In the center, it's sort of okay if you use the log normal. Now, the goodness of fit measures over different measures. That's a log likelihood. That's the Akiki, the Bayes information, Kolmogorov-Smirnov, Anderson-Darling, Kramer-von-Mises. And you see the values are pretty much the same. They're very much the same. In other words, it seems as though when I use one of them, does not really matter which one I use. If I look at the VAR estimates, then you see they can differ quite substantially. For instance, if we use a burr, we estimated at 8,400, while if we use a log normal, we get 5,200. Log normal is, of course, a much thinner tail. And then if we splice, we get something in between. But there's quite some difference. The EVIs corresponding to those two are 0.79 and 0.73, not substantially different. The log normal, of course, has an EVI of 0. We know that beforehand. Okay. If we use a multiplier, then we have to choose K or P star. Remember, that's the free parameter that we have, how deep we want to go into the data. But choosing P star is similar to choosing K or K star. And if we take P star as 0.1 or 0.05, we found that's quite a good range within which to use for P star. They still differ, but to less an extent than we get over there. And we get an EVI of 0.8122. Okay. So it seems in that sense, we're doing quite well compared to the traditional methods. We also looked at the variation, the amount of variation, which was simply okay, I'll finish off. A resampling of 1,000 times with replacement. You just resample. We use the perturbative method, which turned out to be the best of those in a parametric sense with a 0.999 var and the distributions. And for the non-parametric, we use our multiplier with a PA2. In other words, the perturbative second order with those two. Okay. And if we look at the results, those are the two perturbative, 0.1 and 0.05, and these are the three severity distributions we assume. The log normal has the least variability. Quite interesting. Gives the least variability. But overall, this is what we get. Now, I didn't say more on the simulation. We did a lot of simulations on the performance. And for that, I want to conclude with point number 3 there, that the performance in simulation was very good, especially if we combine the second order perturbative with the second order EV. So that turned out to be the best combination that we have. And then just to emphasize again, it's non-parametric. So we don't have to worry about the parametric severity underlying distribution, and it's computationally very inexpensive. Just plug it in, and there you go. And what else we do? Well, of course, these things are always multivariate. You have different business lines and events and so on, so you want to put them together. What I often do is just take weighted averages of different aspects, but you can probably do better than that in a multivariate way. And then one could choose P star in perhaps a bit more automated way. Oh, that's something to think about. Some references, and then thank you. Okay.
The estimation of the density, the derivative of the density, that's such a high quantile. I've never seen this being studied.
Yeah.
It would be, I think, another interesting, like we use the POT method to replace the density.
Yeah.
So we don't go with
Yeah.
density estimation.
No, because there's not data really there to do
No.
density
So it's gonna be
estimation.
interesting to see how.
Yeah,
that works.
yeah. I must admit, I just sat down and did the maths. Because we needed something. And I thought, well, let's try it. But I didn't do the simulation. Others did the simulation, and it turned out to work pretty well. So I think there's work to be done on studying that for this.
You also do web test your model, web test. In order to see whether your bar model is correct.
Yes, that's part of the simulation.
The marginal simulation is a variation.
We simulate from the loan description, and then we start to look at the relative. And that's one of the reasons we come to the.
Yeah, and again, so because we have to choose on this case, then also the fees bar.
Well, they can put the other one.
Okay.
Also, it's not, but in the extreme value theory, the choice is but we all come up with a confusing point. But that's why I'm making that.
Maybe just another comment. We know that bar is not a coherent risk measure. So ideally, one would do expected shortfall or conditional value at risk. I mean, it would be interesting to look at how you can this one. Yeah. Thank you.
My interest, people will see.
Actually, the starting of the file, the one will that the style